Okay, so hello, this is my presentation. I'm Aurin Sarcar from period 5, and I want to talk about how linear systems can be used to represent 3D vectors in a computer. So I think linear algebra is at the core of computer-generated 3D displays, and every polygon in a 3D object it can be represented as the intersection of some number of vertices, which can be treated pretty much as vectors. And so by treating these vertices as vectors, we can pretty much apply clever transformations to create animation effects like motion in a 3D space, or things that look like motion in a 3D space but are actually happening in a 2D space because, they're on our screen. So here I have a little example. We have this green hand, not very well drawn, but I tried my best. And here it looks rounded, but on a computer it would look something more like this, where everything is a couple vectors. If there were more vectors, it would look smoother, and if there were less vectors, it would look less smooth, etc., etc. So I won't do the whole hand here, but you understand the idea. Basically, each rounded edge is actually a bunch of sharp vertices, and if it's very round, there's so many that you can't see them. So it would be like that. But anyway, the reason I'm drawing this hand is because in a computer, you might want to do an animation with a hand, and that hand might be represented in this 3D space. And if you take one vector from that hand, for example, let's take this, that would be about here. Let's see, that looks to be about, let's say it's like negative 5x plus 4y, and let's say like negative 2z. Obviously, that's that might not be to scale, but yeah, let's use that vector to say we're representing one vector in the finger of this hand. Now, I think we should take a look at a very simple case first, where we take a random vector from a 3D model and say it's represented like we have, and we'll say this corresponds to the standard basis of R3, and let's say there's some motion in the X, Y, and the Z axis, and let's say this hand moves up a little bit, right? Let's say instead of facing like this, we change it to face like that, or like that. Let's just take an arbitrary new basis to represent how its orientation has changed. So let me go ahead and make one of those real quick. Let's say it's 10, 20, 50, 3, 4, 20, and 2, 8, 50. Now, with this new basis, we might want to represent our old coordinates in this new basis, and the way we can do that is by using change of basis. So let's write down the very general formula the very general method for a change of basis. So to get P of basis C from basis B, that would be equal to, here we'll start with the formula like this, and what that says is that this change of basis matrix is pretty much going to take the representation in its own basis of all the vectors from the old matrix. This will go up to B, and but for us, n will be 3 because we only have 3 vectors. So let's say we want to put something in terms of C. This would be our C, and well, it would be a set. not. And our b would have been the earlier base, which will just be the standard and so if we want to go between these, what we have to do is we have to transform all of these into those. And that's going to mean we're going to basically multiply all of these old vectors in our basis B with the corresponding transformation in basis C. So let's say we're going to create this augmented matrix basically, where if we want to find PC from B, then we're going to do C1, C2, C3, augmented B1, B2, B3. And that's going to look like 10, 20, 50. Let me just get these vectors down here. Augmented with 1, 1, 1, 0, 0, 0, 0, 0, 0, 0. Now you might be wondering what we have to do to figure out the change of basics matrix, and what we have to do is we have to make this ironically look like that. We have to basically make it into the standard matrix for R3. So let's pretty much get to that. So we'll divide the top row by 10. This row stays the same, and we can divide the bottom row by 2. So if we divided the top row by 10, then it becomes like this, and we divided the bottom row by 2, so it'll become like this. Then we can go ahead and subtract 3 of the top row from the bottom row here, or sorry, from the second row, and then we'll subtract it once from the bottom row. So that'll give us minus 6 would be -2, and minus 15 would be 5. And then we'll do the same thing on this side. Now with this, we're almost done. Let's go ahead and multiply these two bottom rows again, because I think that'll be much easier. And go ahead and get them to have leading ones. So that would look like, and we'll actually make the bottom one negative so that we can just add in the next step and be done, or almost done. So that'll be 1 and -5/2. And since we multiplied it by -1/2, then we have to multiply all these things by -1/2. So that would be -1/2, and this would be 3/20. Then this would become 0, 1, 10. This would become -1/20, 0, and 1/4. Now with that, we're almost there. Did I misplace them? No, okay. And then our the step that'll get us all of our, I think almost all of our leading ones. 1, 2, 5, 1, 10, 0, 0. 3/20, -1/2, 0, 0, 1, -5/2. And this become, so we're subtracting, we're doing R3 minus R2, swap with R3. So that would become like this, and then 10 minus -5/2, which is 20/2 minus negative 5 over 2, which is 20 plus 5 over 2. And that would be, for here, that would be negative 1 over 20 minus 3 over 20, so negative 4 over 20. 0 minus negative 1/2, which would be 1/2. And 1/4 minus 0, which would be 1/4. So here we go. And we're almost done. Now that we have all the leading, this might become a little bit tricky because of the matrix we started with, but that's no matter. This is what computers will have to go through, so we'll go through with it as well. So now we have to multiply this by 2 over 25 to get that final leading one. And that means we have to multiply these by 2 over 25 as well, which gives us 500 in the denominator and 8 in the numerator. 2 over 50 and 2 over 100. Actually, for the sake of ease later on, I'm going to go ahead and, okay, I was going to say I'll put everything in terms of 500, but maybe I won't do that actually. Yep, now we have that, and let's go ahead and get rid of the leading one for x3 there. Or sorry, let's clear out that row basically is what I was trying to say. So that'll give us so we would have added row 3 to row 1 5 over 2 times to get rid of that 5 over 2. So that would be that would be 3 over 20 plus, and we'll do this math a little bit later, 3 over 20 plus negative 20 over 500. I'm going to go ahead and move this over. So 3 over 20 plus negative 20 over 500. Then it'll be negative 1/2 plus, and that would be that should be 1 over 10. And then finally we've got, let me move it again, it's pretty big. And finally we've got, it should just be 5 over 100 for the last one. And then above that, we did it plus 5 times, which will be much easier to calculate. So that'll be 1 over 10 plus negative 40 over 500. Oh my gosh. Over 500. Then the rest are just straightforward, just multiplying by 5. So 10 over 50. And that'll be 10 over 100. And then we can go ahead and simplify those real quick before we go on, because these are some hefty fractions. Should actually put yeah. So 1, 2, 0, 0, 1, 0, 0, 0, 1. Line down there. And this will be so 1 out of 10 will be 50 out of 500. Minus 40 will be 10 over 500. let's go ahead and erase that parentheses. Then 10 out of 50 is 1 over 5, and 10 out of 100 is 1 over 10, and we'll actually go back to 10 over 50, 10 over 500 and make that 1 over 50. Then 3 over 20 plus negative 20 over 500 is, that should be 75 over 500 minus 20 over 500, which gives us 55 over 500. And if we divide both sides by 5, that'll give us 11 over 100. So 11 over 100. And negative 1/2 plus 1/10 is going to give us, that'll be negative 5 over 10 plus 1 over 10. So that'll be negative 4 over 10. And then 5 out of 100, we can simplify that to 1 over 20. And then the rest of our fractions will remain the same. So we'll just go ahead and write those down. Okay, so now we have one more step. Oh my gosh, thought we were done. That's 1, 1, 1, 0, 0, 0, 0, 0. And the way we achieve that is by doing R1 swap with R1 minus 2 R2. So that would be, let's write down the row that didn't change first. Actually, I totally forgot to simplify those fractions, so we'll do that in this step as well. If we're dividing this by 4, then it becomes 125, and this will come to 2. And 2 over 50 is 1 over 25, and 2 over 100 is 1 over 50. And let's continue. We got 11 over 100, negative 4 over 10, which is negative 2 over 5, and 1 over 20. And then up here, we're going to do subtract 2 of these. So that'll give us, if we subtract 2 20ths from 1/10, that's just 1/10 minus 1/10, which will give us 0. If we subtract negative 2/5 from 1/5, that'll give us 1/5 plus 4/5, which will give us 5/5, so just 1. And if we do 1 over 50, which is 2 over 100, minus 2 of 11 over 100, that'll be 2 minus 22 over 100, which will give us negative 20 over 100, which is just negative 1 over 5. So let's go ahead and write that down. And now we're done. We finally have our change of basis matrix, which will be these 3 vectors we have right here in one matrix. So negative 1 over 5, 11 over 100, negative 2 over 125, 1, negative 2 over 5, and 1 over 25, and 0, 1 over 20, 1 out of 50 equals P for C of B. Now, finally, now that we have this, we can go ahead and take this original vector that we had here, and let's copy it. And like we said, if the hand turns, what we want to do is we want to basically have a basis that's kind of following the hand in this original orientation that it has over here. Because let's say we want to shoot like sparkles directly out of a finger, and so we want this exact direction. But we only, like the only vector that we have is this vector in the finger, and we want it to come straight out, so we want to basically do something that follows this hand's orientation rather than follows the orientation of anything else in whatever animation the hand is a part of. Like let's say it's a video game, we don't want it to be corresponding to the environment or aligned with like the ground. We want it to be aligned with the finger because it's magic, and you know, gravity's not affecting it. So let's go over here and let's do P, C, B times this vector, which copied it. So let's go ahead and do this, which, just to be clear, what we're basically trying to do is P C over B, C from B times this X in B to get this X in C, like we had here in the original formula that we wrote down here. So we're trying to represent that old vector in this new basis. So let's go ahead and do that. This will be equal to -1/5, 1, 0, 11 over 100. Oh god, this is going to be not very fun to work with, but wow, I really chose a very, very difficult matrix. But sure, let's multiply that with -5, 4, -2. See, that's an easy vector. So that'll be -5 over -1/5, which is going to give us 1, plus 4 times 1, which is going to give us 4, and then 0 we don't have to worry about. Then we'll do -5 times 11 over 100, which will give us -55 over 100. Then 4 times -2 over 5, which is going to give us -8 over 5. And then we'll do -2 over 20, which is going to give us 1 over 10, -1 over 10, but I put the minus sign there. And then finally we've got -5 times -2 over 125, which is going to give us 10 over 125. Then 4 times 1 over 25, which is going to give us 4 over 25. And -2 times 1 over 50, which is going to give us -1 over 25. So this is all going to be equal to, let's go ahead and simplify some fractions for the last time. Good gosh. We know the top is going to be 5, but then -55 over 100 is going to be -11 over 20. Plus -8 over 5 is going to be it's going to be -32 over 20, and then this is going to be -2 over 20. Then 10 over 125 can be 2 over 25 plus 4 over 25 minus 1 over 25. So that's convenient. And that's going to give us our new vector of 5, and then -11 minus 32 plus 2 is going to be -11 minus 30, which is -41 over 20. And then 2 plus 4 minus 1 over 25 is going to be 5 over 25, which I'm just going to write as 1/5. Equals xc. So now that we have xc, let's say we want to, like I was saying earlier, shoot the magic out of the finger. We can basically tell the computer, here's this old vector, and here it is in the coordinates relevant to the hand, and you can go ahead and generate this effect along that vector pretty much. And yeah, also just to give a quick explanation on how it would generate across that vector, if we're working with like a bunch of pixels, this would probably take basically this small number of pixels and say, oh, generate this here for at this many pixels from the origin, or from like a set point, and then basically wait for a step in the programming, which basically means like there will be like a bit of time before the next step occurs, and then it'll say use that same increment, go do it again, and then go do it again, and basically over like a couple frames it'll generate like this, like kind of how I'm doing it. And since it's following that same, since it's adding those same increments, it's basically ending up following like a literal vector, as opposed to where the hand is more of like the vector is used more to represent the hand, but the actual thing that it's using is like a line segment and not a vector. This would actually like happen across a vector. All right, thank you for listening. I think I'm way out of time.